So now that we have finished the results and looking at them in AFNI from 3D Deconvolve, let's go back and finish the proc script. I'm going to close a couple of these windows. I'll close the time series and the clusterize. I'll close, and I'll just close all of controller B. And we can look at what we need to later on. So now the screen's a little bit cleaner. I'll go back to one axial image here for controller A. So great. Let's see what else happens in the proc script now. Note that if you had added the option regress reml exec, we would probably not look at the 3D deconvolve statistics. We would look at the 3D reml fit statistics. So when we run 3D deconvolve, it actually creates a reml script. If you look at, if I do ls in my results directory, we have stats, well, ls-l stats star. We have the stats brick and head file here, but then there's also this reml command. This is generated automatically by 3D deconvolve, and it shows the 3D deconvolve command there, and then it shows corresponding 3D reml fit command. So if you wanted to account for temporal autocorrelation in the noise model, you could run this script. And if you add dash regress reml exec to the AFNI proc command, that's what it will do. It'll just run this little stats command script that was created by 3D deconvolve, and that's going to take the matrix that was generated by 3D deconvolve and apply it to the data. Note that in the matrix, this is the censored matrix. There's some text in there. There's header information in this 1D file that specifies which time points were censored and stuff. So the input is the same scaled data sets, and then you'll get stats, reml, and variance, etc. But we're not going to do that. So let's see what else is done with the proc script. We're currently on, say, line 352. You see in the corner there, and that's out of 512. So there's another 160 lines to this script. A lot of QC computations for the most part. It uses 1D tool to show correlation warnings in the X matrix, and then saves that to out.format warn.txt. But if we just ran this ourselves, we can copy that line and just paste it into the terminal window. These are all the pairs of regressors whose correlation is 0.4 or greater. And in our case, there's only one pair, and that's the regressors of interest. So should we panic? Yes, of course, we should panic. It's always fun to panic. Once you're done, we can think about whether this is a real problem. If I go back to 1D plot, let's see. Sure, this is great. Those are the two regressors of interest that generate that high correlation. And what does correlation mean? More logically, it means predictability. And if you look at the two regressors, do they help predict one another? Yes. If the audio regressor is high, the visual regressor is almost certainly 0, and vice versa. So that's a high degree of predictability in a negative direction. If this is high, that's low. If the auditory is low, the visual is high. So they are predictive in a negative direction. So there's a correlation of negative 0.612. Are they correlated enough where you're close to a multicollinearity problem? Well, we should have some idea. Maybe it's not in the script yet. If we plot that, this is literally the sum of those two ideals, if you add them up. And if someone's worried about multicollinearity, this is what I will want to see. And what this shows is that even if you add up all the regressors of interest and have them similarly scaled, the sum still has a lot of variance in it. And so you will easily be able to tease these apart. So the correlation is pretty high, or at least the magnitude is high. It's fairly negative, but anyway, it's greater than 0.6, but there's still a lot of variance left in across the regressors of interest. Well, it shouldn't be. It should be across all regressors, really. But there, you won't have any trouble separating which is an audio response and which is a visual response. So, no, the 0.6 is not concerning. And I'll cue to close those. So getting back to this script, so that was the correlation warnings, and they're warnings. They're not 1D tool doesn't know whether they're a problem. It's just the correlations are fairly high. The next thing it does is it runs 1D tool again and looks at degree of freedom information, DF info. That is really mostly focused to, the point of that is mostly to make people doing resting state analysis with band passing nervous. So if you're band passing, that can, depending on your TR, if your TR is say 2, which ours is in this case, that's going to take out 60% of your degrees of freedom off the bat. That's without censoring, without any pull alerts, without any motion, anything. If your TR is faster, like 1 second, it will take out 80% of your degrees of freedom. And then you can see quickly that if there's any motion censoring, you're going to be right near 0 remaining degrees of freedom, or in some cases it will fail because you've gone negative in some sense. You've got more regressors than you have time points remaining after censoring. But we have tasks, so and even if some people that have resting state aren't band passing, so that's not a problem. Here's where we simply create a convenience data set for plotting, and this is what we actually used in the clustering to make our mean time series, and we actually used it in controller B too to look at all 3 runs together. We temporally concatenate the scaled data sets to make an all runs version. So that's just one data set contains all 3 runs. That's just for looking at the data. It's a convenience. Here's a QC step. We create a TSNR volume, temporal signal to noise average, and so we run 3D tstat on the all runs data set and compute the mean. So the mean of all runs, and we save that to a signal time series that we're going to delete. That's why the arm is there. And note, remember the mean should be 100 for all these things, all these voxels that are actually not identically 0, because we scaled them to be that. But just to be complete and cautious, we compute the mean anyway. And then we use 3D tstat and compute the standard deviations of the residuals. And note that we're ignoring, this is the KTRs, the keep TRs, keep time points. We're ignoring the censored time points, the censored volumes here. So we get the mean and the standard deviation of the noise, and then you just take their ratio, the signal to noise, signal divided by noise ratio. And we mask that. The only reason, it's not too important to mask that, but you generally don't want to see the noise outside the volumes. You're really, when you're looking at a TSNR volume, really care if you care about what it looks like within the brain. Well, I guess you care about outside the brain too. Maybe masking isn't a great idea there. Oops. If I briefly look at that, where's the AFNI controller? I'll just leap to that for a moment. We can set our overlay data set to be the TSNR.subjectID, and it's all red. That's beautiful. Let's scale this. 12 is not a useful scale for TSNR. Let's leave it at auto scale, and you see that the voxels we're looking at in here, we're in there we're at 300. In the more interior part, we go to 150, and then 54 in some mid-sagittal CSF regions. So anyway, this looks great. And notably, this is sort of a measure of how much variance is in the time series uh, relative to well, it's exactly the variance in the time series relative to the magnitude of the signal. So, are you going to be able to detect anything useful here? So you want a higher number. You want low fluctuations relative to the signal. Then we compute and store a global correlation average. So this global correlation average is literally for every two voxels in the mask, in the full mask volume, for every pair of voxels, you compute their correlation, and then you want to average those together. So this is a huge number of voxel pairs. Fortunately, correlations that's a linear computation, so we can actually scale the residuals by the variance, so make the variance equal to 1, scale them down so that they're unit vectors. So the sum of the squares is 1. And if they're unit vectors, then the correlation is just a dot product, and then you can just average things very quickly. So from the unit vectors, we can average those over the mask using 3D mask av, and this is the average unit vector, and then we just take the sum of the squares of that unit vector, and that's the global correlation. This out.gcore.1d will literally be the average of all out.gcore.1d will literally be the average of all the paired voxels within the mask. So 0.06. So that's a low G-core. When it gets above 0.1, you start worrying about if there are motion artifacts or other artifacts in the data that are suspicious. Similar to that, we compute a global correlation volume. So that is, forget the unit stuff, but just take the average of the residuals across the mask and get the mean residual time series, and then then correlate that with the rest of the. So take that average and correlate that with the rest of the residuals. And so after the regression, do we see strong correlations remaining in the data? And we'll call that core brain. So just to plot this briefly, the mean ERTS 1D plot mean ERTS.1D. Beautiful, I have no idea if that's important. So I'll close that, and then we can look at it in AFNI. Remember, if you lose your AFNI window, you can actually right-click on the display, the DISP button in the lower left corner, and that'll raise the main window. So let's set our overlay data set to be core_brain. And it's beautiful. We see absolutely nothing. Well, we're thresholding at 4.11. Let's just drop this down. And so then the question is, how much, is there anything in here you have to worry about? We'll scale this back up to 1. You see structure left in there, so there's stuff happening in the data that we're not modeling, since this is in the residuals, and it follows the structure a bit. So there could be a question: do you want to do a better job modeling? So breathing artifacts or things like that. So where are we? Next, I should move. This is weird to have this here, but anyway, we should do this way up above. But we create a fit time series data set from all runs in ERT. So this is where we wanted to save RAM and the 3D deconvolve command above. So we just take the all runs and the ERTs and subtract them, and that's the fit time series. And that's what we used in the plot, the data set number n double plot, where we had the blue fits on top of the black data. So this is where that data set was created. Normally it would be created by 3D deconvolve, but we create it later here just to save laptop RAM, since this was from analyses we would typically run in a class setting. The next thing here, we create ideal files for fixed response stim types. So there are two of them. So the proc script uses 1dcat just to extract from the uncensored matrix ideals for the visual and audio stimuli. We looked at those. Extract non-baseline regressors from the X matrix and then compute their sum. So if I'm looking at someone's data and they're having trouble, they're wondering why their statistics aren't looking like they expect them to be, I will look for strange things in their regressors and their stimulus timing, and this is one place that I look. So here we take 1D tool, we take the no sensors, and we just we separate all the stimuli, the regressors of interest from that. And then we can take 3D tstat and just add them up, where the input is that the output from the prior command, and we add them up and we call this sum ideal. And that's what we had plotted before, 1D plot sum ideal. And that's a nice regular pattern that looks beautiful for our condition. We should have a regular pattern, 20 seconds on, 10 seconds off. We should see a fairly consistent pattern in this. That looks great. If there were gaps in it where it was 0 for a long time, I would worry about missing events. If one particular spot went way up, so this is peaking at 1 everywhere. If at some spot we went up to 2 or 3 out of the blue, I'd worry about messing up the stimulus timing files. I'd worry that there was a mistake there. You can't describe everything you would look for in that, because there's always something else that could cause strangeness. So you just get used to, you just practice looking at the data, looking at these things, and get a feel for what seems like it's okay and what might not be okay. Then there's blur estimation. So in both here's the EPI time series, so we compute the blur estimation in the all runs data set, and then in the residuals, and we do that per run. We compute the residuals per run because we don't want to, this uses we don't want, well, this is a little odd, but we actually do detrend this at a higher degree than 3D convolve used, and again, we'd rather not cross run boundaries with that. So it also keeps the polynomials much more smooth to be shorter units across individual runs. Anyway, then we compute the ACF parameters and we store them in these files underscore APF files. So if I briefly do ls on that directory, I see a bunch of things. And I'll open one of the PNG files. So let's just say, how about, actually I'll just run AFNI just for kicks. Files, and then let's just look at the first one. So this is an image that's showing the ACF estimates for this one run. And so the black curve is, these are correlations at farther and farther distances. So the correlation when at the central voxel should be 1, and then as you get farther and farther away, it should drop off. And so you see this is an autocorrelation function. The black curve is estimates as you get up to, in this case, 17 millimeters away. In the olden days, the olden days being just a few years ago, we used Gaussian kernel for this. We estimated it as a single Gaussian, which is something e to the negative r squared, so times some constant there. But it was just a negative exponential here, and that's the green curve. So that's a simple full width at half max Gaussian. But the mixed model autocorrelation function uses both a quadratic and a linear exponential term and you see that's the red curve. It fits the black curve beautifully. So that's a much better accurate estimation of the autocorrelation function. So this is what we get for ACF parameters, and the parameters are, the first term is the mixing value, a value between 0 and 1. It says what fraction is the Gaussian curve. What's the quadratic decay, quadratic exponential, and implied by that is the 1 minus that is the linear term. And then it gives the denominator values for the quadratic and the linear term. So the ACF parameters here should be 0.66, 3.12, and 12.29. And I'll close this new temporary controller, and I'll just cat this file. It's a simple text file. Here's where that stuff is measured at radial distances that are going up to 17 millimeters. So it's doing the correlations for the terms. Anyway, so now in the now running 3D full width at half max, that we are creating these blur estimate files, blur.api.ts and blur.erts. And later on, we grab the stuff we want to and we store it all in blur_est. But so, for example, if I cat blur.erts.1d, here it's showing you the full equations with the 3 parameters, and then an extra one, the full width at half max for this fit. So this is for the ERTS, and a similar one for the EPI, and then they're combined in blur_estimate for subject FT. And across all volumes and all 3 runs, the EPI time series autocorrelation function blur estimates are these 3 parameters. Those are the 3 parameters you would average across subjects for doing cluster correction, for example. The full width at half max is a separate issue. And then in the residuals, this is the one that you'd actually apply, not the API time series. In task, you'd use the residuals, and you'd take these 3 parameters. And then we're getting to the end of the script now. Now it's generating some more scripts for QC purposes. Here's one that I won't look at. It's just going to review the original EPI data. GenSS review scripts, however, does much more. It generates quite a bit of information. We specify the motion and outlier limits for censoring, and we actually even create a JSON file of review variables. But generate, well, let's just do ls-ltr. That generates, so it was after the EPI review, it generates this JSON file, and then this review basic script, a driver script, and command script. The basic script, if we ran that, that's what does, that's what generates basic. That's what generates the text output that we saw at the end of the proc script. You can run it with / or tcsh, whatever you like. And then the driver script, I will just run that very briefly. If we run this is what we used to use for, well, what we can still use for quality control when you want user control, when you want to look at the data. So it does things and then tells you what to look at. So it runs the basic script and says, I'm running the basic script. Look over it and decide if you're happy. Then you hit OK when you're done. Now it says to review the plots. Colored TRs are censored. It shows you the sensor limit, and the green lines going up are at time points that do get censored. So you see this other motion spike here. This is the enorm plot, FT enorm. Doesn't quite hit the red line, so it's not censored. Again, notice how clean the outlier plot is compared to the motion plot. So it tells you what to look at. Here's the motion stuff. Decide if you're happy with it all. These are the motion parameters plus the enorm and outlier plots. And then close the opened windows before hitting OK to move on, so that you don't have a million open windows at the end. Now you're going to review alignment. I'm not going to read this for you because we can read, but it says you set the underlay to be the anatomy, the overlay to be the EPI, and then it says to turn off the overlay either using the O key in an image window or toggle it off up here, and then to peruse the dataset by going to places and hitting the U key to toggle which dataset is shown as the underlay. So we jump between the volreg base and the final anatomy. And again, we want to make sure that the small CSF values, the dark CSF and the T1 match the bright CSF and the EPI, and all the contrasts are inverted. So we want to make sure the patterns match. You see this blob here is really nice, and then there's this more U-shaped region over here that matches this. That's really nice. Those are the sorts of things that can help you determine left-right symmetry issues. Anyway, this registration looks fantastic. See how this dark part curls down here, and if I invert it, it's just right on top of that. Here's ventricles right on top. So this looks great. So if we're happy with that, we can close it and then hit OK to move on. The next thing it shows is regressor warnings. Here's degree of freedom information. These appear in the terminal window where we ran the script. Are there any degree of free issues? Are we down to 0.02% remaining? No, of course not. So we're good. Are there any regression warnings from 3D Deconvolve? Nope, it's empty. Are there any tent warnings? Nope. I won't go over these in detail right here. You can send me email or a message if you want to discuss things if you're seeing them. And then correlation warnings. These are the things we saw before running that 1D tool -show format warnings. And again, this is the -0.612 that we looked at before. So, and then when you're happy, you hit OK to move on. We see our regressors of interest in the sum. So these are the two stem ideals, and this is their sum. Does anything look bad here? Nope, they look great. Quit, OK. Then it shows us Bob briefly. This is the kind of the final finish here. It just opens up the full fstat. It sets the overlay to the final stats data set, and then the volume is the full fstat. And it just thresholds it at 90%, and do your main stats. This is regressors of interest against the baseline model. Are your regressors of interest explaining variance where you want them to explain it? Does this look like it ought to? Yeah, I see big visual blobs and big auditory blobs, and that's fantastic. And that's it. And this is a live AFNI controller. You can do what you want here. You can open a new controller window, set the underlay to be, I don't know, all runs if you wanted to look at a time series in this location, whatever. This is all live, but it's just being run by this script. So this is driving AFNI with this script. And now that I'm happy, I'll close this. We can cheat and hold the shift button down while we click done, and it closes all of the windows for that controller. And we are good. So that's the SS review script, the driver script. The command script, I'm not going to run that with driver commands. I'm not going to run this, I'm just going to cat it. This is a fairly short script. This is basically the exact commands that are in the driver script, but saved in a text file. So if you want to view them yourself, how is that driver script showing them? It just has them separated out. It's a little easier to review. If we did less on the @ssreview driver script, this says, well, this has a lot of comments and stuff, but the commands are all separated, so it's possibly a little harder to find things in here. But if you wanted to do this stuff yourself, you could. You prompt the user, tell them something, and tell them to hit OK, whatever. So after that's done, now we do one last thing. One last bit. This is from the APQC, the AFNI Proc Quality Control updates that made by Paul Taylor. So a few commands to generate it, but basically this is going to generate a directory qc_ft. If I type ls here, I see qcft, and if I type ls on that, I see media, extra info, and a main index.html page. So this is something you can open with your web browser. Before that's run, we run ssreview basic one time, just so this is well, actually this is run later on as well, so it's left as the last thing on your screen. Before I look at the QC stuff, I will finish the proc script though. The very last thing in the proc script is a commented section that is basically the AFNI proc command that was used to generate this script. So that makes the proc script kind of useful that way. We can see if there's any shell syntax that may have messed up the command, or if I just have the proc script, I can see what options are applied. So I'll just leave that there, and let me look at this. Let me look at the QC HTML report. So I'm just going to do, I could use Firefox or Google Chrome, or I'll just tell AFNI Open to find a web browser on my system and open the file qcft index.html. And this is the last thing that the proc script output tells you, is to look at this. And here it's here, consider running AFNI Open -b blah blah blah. So I'll do that. And it opens up my web browser with all the sections. I think Paul will probably make a nice video on this, but I'll just run through it fairly quickly. Subject FT, our task is task name, of course. That'll go into the paper. So we're checking the volumes and a ridge space. Simply, does this look good? Yep, it looks good. And we did look at this before. Remember, it's very important to look closely at the data. Does it seem like everything's good? This QC stuff is just a very compact and place where you can quickly do a gentle review of everything. You should review this in fair detail for every subject while they are being acquired. The first couple of subjects, I would say to do what we did in the set of videos, in that you walk through their data and the proc scripts and look in detail to make sure things seem like they're working the way you expect them to. But anyway, now we're doing the quick review here. So here we're comparing the registration between the INAT final and the EPI volume registration base, but it's in standard space. But that's okay. We can still see if the registration looks okay, and it does. It looks like the outlines of the EPI are following the sulcal patterns of the T1 underlay. I kind of prefer looking at doing the U toggle key view myself, but this is a nice way to at least have a quick idea. If it were off by half a brain, you would know it, obviously, right? You can even detect left-right flips in these views. Here we're checking a similar registration, but the INAT to the template. So how do the template edges look on top of our subject's T1 here? Looks good. Doesn't look great. And remember, we used affine registration instead of nonlinear, so nonlinear registration should look much better. Does nonlinear registration to the template affect your single subject results? No. That just they're spatially distorted and shifted and stretched and whatever. They're moved around a little bit, but the blobs are basically the same. What this affects is the group analysis. If you align your subject's API to the anatomy well, and you align the anatomy to the template very well for every subject, that means that the API data is aligned across subjects very well. And that means your single subject blobs, assuming they are anatomically specific, should overlap well. So you should get better group results using nonlinear registration. But the single subject results should look about the same, just slightly spatially distorted versions of each other. Here are the full F-stats, maybe a prettier view of them that we saw before. That's a very clean image. In some cases, you'll notice some of the subjects' results look very noisy here, and that just means they're full. There is a lot of variance remaining in the data. Here you're looking for motion and outliers. These are prettier plots. This is the Pythonic form. Instead of using 1D plot like we had been, this is using 1D plot.py to make it's got the prettier labeling. It's got the stuff on the right that shows the where most of the values are, and the censoring lines, and even the white and darker spots to show run breaks. So that's great. The motion parameters looks very nice. Mentions the censored volumes. There are 4 volumes here, plus 2 more, so a total of 6 volumes were censored, 6 time points. Regressors of interest, this is the sum ideal. The individuals, remember we saw that part of this was cut off in the X matrix due to censoring. And here's the degree of freedom information in case we're doing band passing and censoring and resting state, and we should panic over that, but we're not, and so we don't need to. Here are the the global correlation against white matter. The whole brain. I'm sorry. This is the whole brain average with the ERTs. So the core brain volume that we looked at briefly in an earlier video. It's okay. We expect some residual correlations left in there. Again, a lot of that will be to respiratory and heart blood pulsation effects, cardiovascular. The Grey plot along with the E-norm, and then some of the warning files that we saw. Matrix correlations, there's a mild here, that's even slightly pink up in the warning section there. Doesn't say there's necessarily a problem, but you should think about it. You should think about whether or not it does seem like a problem. The censored fraction, we only censored 1.3% of the time points. The censor fraction per stimulus condition. This is 240 and 239 time points. This is not just stimulus onset time. This is after convolution with that PLOCK curve. So the regressors are on for most of the time there. More than half of the TRs. That just when the ideal regressors are non-zero. No pre-steady state warnings, so it looks like the pre-steady state time points have been removed. Should we worry about left-right flip problems? It looks like it's okay. There's no warning there. The original value is lower than the flip value, so if the cost function is lower, that means they're better registered in the original case versus the flip case. Here's comparing the original and the flip cases. These are the local correlation volumes. So this is the 3 runs from the should be from the TCAT block. There we go, the TCAT up there. So you'd see a lot of motion up there, but hopefully much of the motion has been corrected in the Volreg block, and this is where you're doing local correlations against Gaussian weighted neighborhoods in this case in the volreg results. And that looks fine. If you see some big blobs in here, especially like a big blob in one part of the brain it's not following structural patterns, then you might need to worry about it. If it's, in one case we saw this when Bob first wrote up the Instacore stuff, he saw a big red blob in the data, and it turned out that was a single channel going bad in the at the scanner. And then the last thing is that text output again that shows our final statistics, data sets, the EPI resolution, motion limit, number of time points censored, runs found, total TRs, six time points were censored, the fractions, the temporal signal to noise average 229. We saw the global correlation, maximum f-stat 953. Maximum f-stats are going to fluctuate wildly, so this is not, I wouldn't ever use this as like an important value for my analysis. If it were crazy small, then it's useful, but the difference between, oh, this subject had 500 and that subject had 600, that doesn't tell you anything. And then our ACF parameters that we might use for cluster correction at the group level. So that's the QC output. That's the end of the proc script. So that ends the main part of this analysis, the single subject analysis. I will add on a couple more videos of doing quick AFNI proc things and doing the t-test for our single subject results. This is supposed to be a start to finish, so I'll do that for the finish aspect, and I'll go through the global processing outline as well, which I in the actually attended boot camps at NIH and wherever, we would describe the actual processing steps that we'd run for a complete analysis. Not looking at the data so much like this, but just an outline of all the steps. So we'll get to that in a little bit then.